Hello everyone, welcome to Unit 5, Lesson 5, the second last unit of the course. This lesson we're going to look strictly at graphing rationals and solving rationals with our graphing calculator. This whole lesson's been based around studying different types of graphs, getting used to how to enter them in your calculator and how to solve them with your calculator. Rationals are a little bit more complicated than some of the other functions we've talked about. There's a lot of little bits of information that you'll really want to try and commit to memory as soon as possible, like how to determine asymptotes and how to get domain and range. Very important stuff for working with rational functions. I've got example 1 already worked out for you in the notes. I'm going to work through examples 2 through 5, showing you 3 different types of rationals and kind of give you a few clues on how to handle them, and then we'll look at graphing a couple equations as well. Very first thing that you deal with when you work with rationals and you're having to state domain, range, and asymptotes is to, first of all, work with the non-permissible values. We already know from Unit 1 that x minus 2 cannot be 0. We've worked with restrictions already. We know that we can't divide a function by 0. So same thing in this unit as well. So x in this thing cannot be equal to 2. I'm going to work this through algebraically and then just show you what this picture looks like and verify our numbers. So our domain in this function will mean that x can be any single number but 2. That's kind of the neat thing about finding the restriction. So x will be any real number but 2. That's the one thing that breaks this graph. The other nice thing is, once you find that restriction, that'll be the equation of the vertical asymptote. And this is the case every single time. Domain and asymptote are found by finding the restrictions in the denominator. It's horizontal asymptote and range that are a little bit harder to deal with. And if you look in the notes, I give you some advice on using the degree of the numerator and degree of the denominator to help you find that. In this case, the degree of the numerator is 0. There's no variable on the top. The degree of the denominator is a degree 1 because there is a variable. So when you have the degree of the denominator greater than the degree of the numerator, in my notes, I also tell you that the horizontal asymptote will be y equals 0. And I'll verify that using the calculator in a short minute. And once you know the horizontal asymptote, then you also know the range. Y such that y cannot be 0. It'll be any other real number. I wanted to do this algebraically so that you can look at this and see how the relationship between domain and vertical asymptote relates to your denominator. Horizontal asymptote and range relates to the degree of the numerator and denominator. Now let me graph this, and then we can verify these things with our calculator. So if you want to take out your calculator and graph these as well, kind of follow along with me, we're going to enter the equation 3 divided by, and we have to bracket the denominator, x minus 2. And we're going to graph this just in our regular standard window. So we'll just make sure it's zoom 6. And a couple quick things to note. When you see that vertical line on your graph, that really isn't a part of the graph. It's your calculator has to draw this thing continuous. But what really happens is this graph kind of falls up to that vertical line, and then it starts again at the top and works its way back down. There's a real break in the graph, but your calculator can't do that. So it draws everything connected. So those vertical lines are a very good indicator of where your vertical asymptotes are. You could also look in your table of values to find that asymptote, and I'll show you in a second. The horizontal asymptote is the number, the y value, that your graph approaches on the far left and the far right. So you can see that it's approaching 0 as it goes left and as it goes right. Let's verify that in our table of values. In your table of values, at x equals 2, notice you see error. That's your calculator telling you that that's where the vertical asymptote is. Now, I don't use my table of values that often, just in case my vertical asymptote isn't an integer, then it won't show up in my table. But at least you can verify this. Notice when you scroll up into the negative numbers, it's getting smaller and smaller and closer to 0. I'm at negative 20 and it's negative 0.13. When you scroll to positive 20, you can see that the graph again is approaching 0 from the positive, getting closer and closer to 0. So you can see that horizontal asymptote. If you go back to your picture, this graph goes forever left and right, except it breaks at x equals 2, explaining our domain. This graph goes forever up and down, except it breaks at y equals 0, stating our range. Once you get the hang of graphing these and looking for the little tricks, then rationals aren't so bad, because they don't have a general shape like quadratics and radicals and linears. These things can take on many different types of shapes. That's what makes them a little bit more complicated. So let's clear these equations and get this set up for our next example. So example 2 or example 3, now what we're going to do is look at a slightly different function. It's going to be 2x over x plus 1. But again, start with the denominator. X plus 1 cannot be 0, meaning x cannot be equal to negative 1. There's our domain. X such that x cannot be equal to negative 1. X is an element of the real numbers. The vertical asymptote will be that restriction. X equals negative 1. Now the horizontal asymptote, we compare the degrees. The degree of the numerator is a degree 1. The degree of the denominator is degree 1. Since they have equal degrees, then what you have to do, the horizontal asymptote will be leading coefficient of the numerator divided by leading coefficient of the denominator. So this asymptote should be y equals 2. The leading coefficient of the top is 2. The leading coefficient of the bottom, with the coefficient of x, is 1. So that should mean that the range, y such that y cannot be equal to 2, y is an element of the real numbers. So when you get equal degrees, it's leading coefficient divided by leading coefficient. Let's graph it and see if we get these values. Let's put in the equation. 2x divided by bracket x plus 1. Let's put this in our standard window. And we can see right off the bat that vertical line is at x equals negative 1. That's verifying our domain, and it's verifying our vertical asymptote. You can see that the graph approaches the y value equal to 2, but we could use our table of values to go see it. You can even see on my screen that at 24 it's approaching 1.92. So if you go to say negative 24 and see if you get the same result, it gets closer and closer to 2 on the right. Let's see if we get closer and closer to 2 on the left. And it seems to get closer and closer to 2 as we go on the left-hand side. Again, verifying our horizontal asymptote. Once we know the horizontal asymptote, we know this graph goes forever up and down except for the horizontal asymptote. This graph goes forever left and right except for the vertical asymptote. So look for those vertical lines. Look for that horizontal line. It's an imaginary one, unfortunately, that you have to see the graph approaching on the left and the right. This case, the degrees were equal, so it's leading coefficient divided by leading coefficient. It really helps when you know those 3 little short rules about how to compare degree for finding horizontal and asymptotes. Let's look at the last case that you're going to see with graphing. In this case, we have x squared over x minus 2. And again, start with the non-permissible value. X minus 2 cannot be 0. X cannot be 2. Therefore, our domain, x such that x cannot be 2. It'll be any other real number. The vertical asymptote will then be x equals 2. Now when you compare example 4, the degree of the numerator is a degree 2. The degree of the denominator is degree 1. So when the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote, which means the range will be a little bit harder for us to find. It doesn't mean that it's going to be all real numbers. You're going to need your calculator to figure out the range in this one. Don't just automatically assume that because there's no horizontal asymptote that the range is all real. And you'll see that when you look at this picture. So we'll get the range from our graph. This is a popular function, by the way. Let's put in y equals x squared divided by x minus 2. Graph it. And notice that this is a slightly different picture. You can see that we do have that vertical line at 2. So we are going all left and right of that. Looks like there's a top piece and a bottom piece. But it isn't that it approaches just a single line. There's just a whole gap in here of values of y that we can't use. Now, what we can do is we can use our calculator to help us find that. We could look for the maximum of this chunk of the graph and the minimum on this chunk of the graph, and our y values will be greater than that minimum piece and less than that maximum piece. So let's do that. Second function trace. Let's go find that minimum section first. And it works very similar to the 0 feature. You move your cursor so that you're left of the minimum. Hit enter. Move your cursor so that you're on the right of the minimum. Hit enter. Hit enter, I guess, one more time. And remember, we're looking not for the x value in this case, we're looking for the y value. So we're going to have y values greater than 8, because it goes up from there. We'll keep that off to the side. And let's go find the maximum. Second function, calculate 4 for maximum, and let's move our cursor so that we're near that maximum. Again, setting our left and right boundary. Left, enter, right, enter, guess, enter again. Oh, this is good that this came up. Notice you get some scientific notation. It's our calculator that's trying to be extremely accurate, but 1.79 times 10 to the negative 6 is 0.0000001. And the y value, negative 1.62 to the negative 12, is 11 zeros. So that's pretty much y equals 0 if you were to round that. So the other value, we have a maximum y value of 0, and it'll go less than that. So our graph will be all the values of y less than 0 and all the values of y greater than 8. Notice it's not a horizontal asymptote. There's just a region in the graph that there are no y values. Between 0 and 8, the graph is undefined. Greater than 8 and less than 0. So let's put that down as our range. So we'll write this as y such that y will be less than or equal to 0 and y will be greater than or equal to 8, an element of any real numbers. So what I'm saying there is y will be any number less than 0 or greater than 8 in this example. This one's a little bit different. It's when you get those types of functions with the degree of the numerator greater than the denominator, you could get a little bit tricky of a function to work with. You'll have to really work with your window settings and your calculator for that domain and range. But I really want you to understand the relationship between domain, vertical asymptote, and restrictions. Horizontal asymptote, range, and comparing degrees of numerator and denominator. Once you get a real good handle on that, rational functions tend to be a little bit easier. Now, example 5, let's use our calculator to do some graphing. Again, we have two ways of doing graphical equations. We can set left side, right side, find points of intersection, which I'll do for the first one, or graph one single equation and find zeros. So what I'm going to do with this first example is graph, first of all, 3 over x plus 1 plus 1 over x minus 1, and then y2 equal to 2. And I'm going to determine points of intersection. So I'm not going to look for zeros, I'm going to determine points of intersection. Bring up the calculator. Clear this up. Let's enter the two equations. We're going to go 3 divide bracket x plus 1 plus 1 divide bracket x minus 1, and equation 2 is 2. We've already got this standard window, so let's just have a look at this picture. It looks a little complicated. Remember, I'm looking for where that crosses the horizontal line. You can see it crosses the horizontal line in the middle. So I'm going to get rid of that far left and far right of the graph. Instead of going from -10 to 10, I think what I'm going to do is go from -5 to 5, just to spread this graph out a little bit better. And that way I might be able to see these points of intersection a little bit easier. Remember, we're looking for where the graphs cross, not the asymptotes. There's an asymptote there at -1 and +1. We know that already because the equation has plus and minus 1 in it. So those are just asymptotes. They're not part of the graph. But this point that I'm circling here is a point of intersection, and this point over here is a point of intersection. Let's go find them. Second function, trace. 5 for intersect. My cursor is right by that point right there anyway. So go enter, enter, enter. The first point of intersection is going to be when x equals 0. The second point of intersection, we need to move our cursor close to it so it doesn't find the same one again. Go enter, enter, enter. I like this point of intersection method because it's quite quick. You just sometimes have to mess around with the window settings a little more than the 0 feature. And the other point of intersection is the point 2. So let's label our answer. We'll say x can be equal to 0 or x equals 2. And if you're going to use the calculator, you have to state the window settings. So I went from -5 to 5, up by 1s, and y was -10 to 10, up by 1s. So that's the method using points of intersection. Same as what we did in the last couple of lessons. The other example, since it's already set to 0, I'm just going to use the 0 feature and use 4x over 3x plus 4 minus 10 over x plus 6. And in this case, I'm going to determine the zeros. So back to the calculator again. Clear up our equations. Clear our history here. And what we're going to do is enter in 4x. Oops. 4x. Start this again. 4x divided by 3x plus 4. Make sure you always bracket your denominator minus 10 divided by x plus 6. Let's go into our standard window. And remember, what we're looking for on this graph is not points of intersection anymore. We're looking for zeros. Well, I can see there's 2 zeros in this case. There's the 1 0 over here. There's another 0 in this area somewhere. Those other vertical lines represent the asymptotes at -4/3 and at -6 are restrictions. So don't include those. So what we want in this case is zeros. Second function trace. Option 2 for 0. Since we're over on this side, let's just look for this 0. Set a left boundary. Enter. Cross that 0. You can see your y values going to the positive. Then you know you've crossed the 0. At guess hit one more time. And the first 0 is when x is equal to 4. Let's go find that other 0. Second function trace. Option 2 for 0. Move our little flashing cursor, I call it a little bug, into that second region. Set a left boundary. Enter. Set a right boundary. Enter. Guess, hit enter one more time, and we get -2.5. So the 2 zeros in this case are -2.5 and 4. You get rid of the graph. X equals -2.5 or x equals 4. And again, state your window settings. -10, 10, 1. -10, 10, 1. That's our standard window settings. Get really familiar with the calculator. It will be a major advantage to you in 30 Pure if you know how to use the graphing calculator to find zeros, to find points of intersection, to understand how to find domain and range. It'll make life so much easier if you can get used to that calculator. Look for some of the key features. Keep practicing until you can find these solutions. What I want you to work on, second last lesson, exercise 5.5. Lots of graphing, finding asymptotes, finding domains and range, and then solving a few equations at the end. Take care, everyone.